So this is going to be a very observationally focused talk, particularly looking at results from ALMA and what they tell us about the distribution of CO and protoplanetary disks. So before ALMA, our maps of CO and protoplanetary disks looked like this, with a couple of beams across the CO disk. And because of this limited spatial resolution, it was really difficult to get observational constraints on any radial structure of CO in the disk beyond there being brighter emission at the center and weaker emission at large radii. Now, with ALMA, one of the first really interesting results to come out for protoplanetary disks was this image of an N2H plus emission ring in the disk TW Hydra. And this was interpreted as being a deficit of N2H plus emission at the CO snow line, which in this image is around 30 AU, with the idea being that because N2H plus is destroyed by CO, when you have a high CO abundance, you're going to have a deficit of N2H plus. Now, follow-up imaging of a larger number of protoplanetary disks showed that N2H plus emission is not always a single ring. And the interpretation for this was that it depends on the physical structure of the disk. So in images where you see a narrow ring of emission, the idea proposed by Chi et al. In 2019 is that you have this thick vertically isothermal region that is bounded by the CO and N2 snow lines, and this is where the majority of your emission arises. When you have broader emission, they interpret this as being a thin vertically isothermal region, so that a large portion of your emission is coming not from between the midplane CO and N2 snow lines, but between the CO and the N2 snow surfaces. There's another paper led by Merrill Van Hoft in 2017 that also discusses additional complications of using N2H plus as a CO snowline tracer. So as for actual observations of CO with ALMA, there have been a large number of surveys of CO emission in protoplanetary disks. And something that is found over and over again is that CO is underabundant relative to millimeter dust. So this could be due to a low total gas mass in the disks, which is shown on the top axis here, or due to a low CO abundance, which is shown on the bottom. But in either case, there is something in these disks that is significantly different from the ISM abundance. It can be difficult to differentiate between these two scenarios since our main mass tracers are dust and CO, and they don't agree. However, in a few disks, we can break this degeneracy using detections of the H2 isotopolog HD. HD was detected in 3 disks with Herschel, and when we use these spatially unresolved HD detections to get disk masses, we find CO abundances relative to H2 that are between a factor of a few and 2 orders of magnitude below the ISM abundance ratio, which means that in every disk where we have this alternative mass tracer, it is the CO and not the total gas, which is missing. Now, a quick word on the utility of HD as a mass tracer. If you're using HD emission to try to pull out a mass, there is a strong degeneracy between the abundance of HD and the temperature you assume, shown here. So this black line shows all of the solutions that match with the observed flux for TW Hydra. And in addition, HD is only going to emit from gas that is warmer than 20 K. So HD-derived gas masses are going to be extremely sensitive to the temperature structure of the disk that you assume. With this in mind, I use resolved ALMA observations of CO isotopologs as part of my PhD dissertation to get a better handle on the radial temperature and CO abundance structure in TW Hydra. And when we were able to map out the CO abundance relative to H2 using Hg as a proxy, we found that everywhere that we detect CO isotopolog emission, CO is depleted with respect to the ISM. We do see some return of CO inside about 30 AU, corresponding roughly to the snow line. Here it's at about 20. I'll discuss that later. But the point is that nowhere do we see the CO abundance returning to ISM values. If we look at the temperature profiles derived from our CO observations, in the outer disk, we find a near constant temperature of about 21 K. We interpret this as meaning that the majority of the CO emission is coming from this layer right above the CO snow surface. So this is telling us that the CO freeze-out temperature in this disk is about 21 K, corresponding to a binding energy of 960 K, which suggests CO binding to a CO ice-coated surface. We can then take this information, since we're not actually looking at the midplane CO snowline, and predict where that midplane snowline should be. So to do this, we solve for the temperature where the rate of freeze out onto grains equals the rate of desorption off of grains. So here we use a binding energy and a CO density based on our observations. And then we compare to a midplane temperature profile from a previous model of TW Hydra. And we find that the likely midplane snow line is going to be between 18 and 25 AU, with the surface CO snow line further out at 30 AU. So this is something that we were actually able to test using follow-up observations of the isotopolog 13C18O. So this is work that was led by Coco Zhang, who showed that in the inner disk, the CO emission is coming from roughly 4 scale heights above the midplane. And even the C18O emission primarily comes from 1 scale height above the midplane. However, your 13C18O emission is primarily coming from the midplane region. We modeled the CO column in the inner disk with our spectral resolution, allowing us to go down to 5 AU, and found a snowline location in the midplane of 22 AU, smack in the middle of where we predicted it would be. So that's for observing midplane snowlines. And in a disk like TW Hydra, which is pretty much face on with respect to the viewer, that's kind of the best that we can do to constrain snowlines. But when the disk is more inclined, you can actually directly observe the CO snow surface. So what I'm showing here are a series of channel maps. And if you're not familiar with these are breaking down the emission into discrete velocity bends. And as you move through velocity space, the location of the peak intensity is going to change because the disk is in Keplerian rotation. And in this edge on disk, you can see emission coming from an upper surface as well as from a lower surface because your disk is more inclined. So you can use this to actually trace the height of the CO emitting layers. So this is done for IM Loop by Christoph Pint and collaborators. And this gap that you see between the upper surface and the lower surface is because of the freeze out of CO in the midplane. So not only were they able to measure the height of the CO snow surface, but also the temperature of the gas, finding a value of 21 K consistent with the value that we found for TW Hydra. Okay, so now I'm going to talk about some preliminary results from an ALMA large program called Molecules with ALMA at Planet Forming Scales, or MAPS. This is a program led by a group of really wonderful women, Karin Oberg, Viviana Guzman, Catherine Walsh, Yuri Akawa, and also Ted. So this is a spectral line survey of 5 protoplanetary disks in bands 3 and 6 with a spatial resolution between 0.15 and 3 arc seconds. And there are a lot of really interesting science results that are going to be coming out of this program soon. But today I'm just going to focus on what we're finding out about CO in these disks. So this is mapping the CO depletion as a function of radius in each disk. This is work once again led by Coco Zhang. And here she created disk physical chemical models and compared the emission in the disk models to the observations, and then found the best fit model based on observations of C1802 to 1 in order to map out the CO depletion as a function of radius, as well as identify the location of the midplane CO snowline in the model. And a couple of trends here. All of the disks have regions where the CO abundance is below ISM values. And in general, you see a lower CO abundance for the disks around T-Tauri stars compared to the disks around Herbigs. Now, here our total gas masses are based primarily on the dust masses and assuming a dust to gas ratio of 100. However, for one of these sources, GM Auriga, we do actually have an HD detection. So what I have been doing as part of this collaboration is building a model that is able to match the HD flux as well as the resolved CO emission for 11 different transitions of CO. So this includes the 2 to 1 and 1 to 0 lines observed as part of the large program, as well as observations from my own ALMA program in band 7 and band 9. Now, whereas in the Zhang et al. Analysis, the CO abundance reduction was carried out after running chemistry in the models, here we're reducing the CO abundance initially, because in these thermochemical models, the amount of CO is going to affect the gas temperature, which in turn is going to affect the HD emission. So this is still preliminary work, but I want to show you a couple of the initial results. So this is our best fit model so far, showing the radial profiles. Black lines show models and blue lines show data. We're getting a total HD flux of 3 times 10 to the 19 watts per meter squared, compared to an observed flux of 2.5 times 10 to the negative 18. And the best fit model here is for a very massive disk with a total gas mass between 0.24 and 0.34 solar masses. For reference, the mass of the central star here is 1.1 solar masses. So this is a large, massive disk. It's also very cold. You can see the 20 K temperature contour here, and much of the mass in the disk is colder than 20 K. This means that our HD emission is primarily tracing radii smaller than 200 AU. And finally, the disk is CO depleted. So this is showing the CO depletion profiles from the Zhang et al. Modeling and from the modeling that I've done. And I want to stress that the final values for all of these are probably going to change a little bit. However, the general trends of massive cold and CO depleted are likely to hold. Now, the last thing that I want to mention is the time scale of CO depletion constrained by observations. So this is a plot showing the CO abundance relative to H2 as a function of system age for a series of disks analyzed by Zhang et al. 2020. And then I've added a couple of points for the large program sources that were not already included. And you can see that by 2 million years, we find a factor of 10 to 100 depletion in the majority of protoplanetary disks. However, if we look at disks that are still embedded in their natal envelope, which are colored red on this plot, we find CO abundances consistent with the range that we observe in the ISM. And what this is telling us is that whatever process is removing carbon from the CO occurs very early on, around the 1 million year mark. And exactly what that mechanism is, I am going to leave to the other speakers today. Okay, so to quickly summarize, we can now directly observe the CO snow surface in protoplanetary disks. If we want to observe the mid-plane snow line, we need to use a rare isotopolog such as C17O or 13C18O. CO is often underabundant in protoplanetary disks, and observations suggest that this depletion occurs early. Thank you.
Thank you very much, Kamber. Virtual applause. So we already have a couple of questions. I'm just going to read them. And if people in the audience have additional questions, please feel free to add them to the Q&A. So the first question is, do you think we'll be able to detect HD in a large sample of disks with SOFIA in the future?
So we would have been able to detect HD in a handful of warm massive disks with the Hermes instrument. However, that ended up not going through. So unless a new instrument that is able to observe at the correct wavelengths is proposed for SOFIA, we're not going to be able to detect HD. Right now, the best bet for detecting HD in additional sources would be the Origins Space Telescope, if that were to be funded.
Okay, thank you. And next question. With the temperatures in the disk being this cold, do you expect that there is significant additional deuterium enrichment processing happening within the disk?
That's entirely possible. And as part of this MAPS large program, we are observing several deuterated molecules, and there is at least one project that is looking at mapping the deuterium fraction in these disks, so stay tuned.
Okay, so another question here that just came in from Sebastian Kreit, who says MAPS is awesome. And he also says, are there any correlations between CO depletion and the behavior of other molecules?
Nothing that is consistent from disk to disk. So I think Arthur is going to talk a little bit about what's going on with C2H and carbon depletion, but we're not really finding general trends in the observed substructure between the different molecules, which is interesting.
Okay. Then a question from Sierk van Terbescha. In a very similar genre, is there any correlation between CO depletion and the continuum features in these data?
So for the MAPS sample, in 2 out of the 5 disks, the CO snow line seems to be generally co-spatial with one of the bright emission rings. But once again, there's no consistent pattern between the CO features and the dust features.
And yeah, somewhat related to that, the values for MDisk based on your CO work seem like they might make the disk gravitationally unstable, this the GM-Auriga disk. Is there other evidence for this in the structure, for example, in the dust?
Not in the dust. You can see this is the 12 CO emission in GM-Auriga, and there are some very interesting non-axisymmetric features in the outer disk. There is a paper being led by Jane Huang that will discuss these. Based on our calculated Tumor Q value for GM-Auriga, there's one region in the inner disk that may be gravitationally unstable, but on the whole, it appears to be gravitationally stable.
Okay. And I think, yeah, we're going to have one more question and then we're going to move on to our next speaker. Lukasz Tikonic asks, how does early CO depletion occur? And how is it connected with the fact that young disks are warm?
I have some thoughts on this that are related to perhaps increased ionization in these young systems. But I believe that we're going to hear a lot more about this from Arthur and Alex. So I'll leave that to them to answer.